Okay, students, now comes question number 28. It says, show that W given by this is not a subspace of R cubed over R. So now let's check whether this is not satisfying the subspace condition or not. So the solution goes like this. Here, it's enough to show that at least one of the subspace condition is going to fail, okay? So let's consider causality property. Take an arbitrary element from W, 1A0. Yes, 1A0 is a vector with 1A0 is part of W, okay? For an element to be part of W, the first entry must be 1, and you are free to take any real number as the second entry, and 0 must be the third one. So 1A0 belongs to W, and take another one, 1B0 is also in W. Now what happens if we take the sum of the two? Look, if I take the sum of the two, 1 plus 1 comes what? 2. Now comes the deviation, you see, happening. For this to be part of W, necessarily the first component must be 1. But here it says what, student? 2. Because of this is not in W, okay? This is not in W. So the given W is not a vector space. A vector space. You see, I mean a subspace of the given vector space RQ. You can also take another approach. Even you can also have this as additional one. Take any real number A here and multiply that by what? An arbitrary element taken from this one, 1y0. If you multiply that, you will get ay0. For any number A different from 1, this is not in W, students. Because if you take A to be a number different from 1, it doesn't belong to what? W. Because of this is not a vector space, I mean a subspace. And that is it. Moreover, the identity element 0, 0, 0 is not in W. You see? So I just brought three different situations where this is not filling out, but it is enough to bring one only. Anyway, this given W is not a subspace of R cubed. So what comes next is the other question number 29. Let you take A and B as you see. Now the question is, do you think that the union of these two can be a subspace of R2? Let's see. Take again here, students, let's consider again the case where you see one condition being failed, and that is, consider for instance this what? Ordered pair 1, 2. Clearly 1, 2 is an element of A, because when you put 1 there in place of x, 2 times 1 is 2, so 1, 2 is an element of A. Take again another element 2, 1, you see, because when x is 2, y can be 1, so 2, 1 can be an element of B. Students, please correct this one by making B, okay? This is B, whereas this one is A, this one is B. Now if you take the sum of the two, 1, 2 plus 2, 1, it will be 3, 3. And we know that 3, 3 is not an element of the union. Because for an element to be within the union, you see, either the first component must be twice of the second one, or the second must be twice of the first. But this is not the case. 3, 3 is not, you see, behaving this kind. Because of this union is not what, students, a subspace. So there is one thing that I would like to tell you as a tip here. Whenever you unite two subspace of a certain vector space, the union may not be a vector space. But this is not true in the case of intersection. The intersection of two subspaces of the same vector space is always a subspace to that vector space, students. So please understand that. And coming to the 30th question, we have this. Show that the following are bases for, you see, the vector space R cubed, and you are also asked to find the dimension of this vector space V. So the given, you see, set is this one, a set containing these entries 1, 1, 0, minus 1, 2, 1, 3, 1, 1. So in order to show that a given set of collection of entries is a basis for a given vector space, what we need to do is we have to show two conditions. 1, you see, the given elements must be linearly independent. 2, the given elements must span or generate any elements within what, students? Within the given vector space, or every element within the given vector space must be generated by the what? The given elements in the set. That's why we call them bases. So let's now check the first condition, that is to say the linear independent case. So take arbitrary three coefficients A, B, C from the set of real number, because we are having three elements here, students. Because of this being 3, we are going to take three coefficients a, b, c. Now let's take the linear combination of these 3 and equate with 0 vector. So as you see, a times 1, 1, 0 plus b times minus 1, 2, 1 plus c times 3, 1, 1 equals 0 can follow. And from this, what comes is this one. If you simplify this, students, a times 1 is a, and here minus b and 3c. So a minus b plus 3c can come. This is a plus 2b plus c can come. And here, this is 0, and this is b and c. b plus c equals 0 can follow. So this has to be what, students? This has to be equated with the 0 vector. So if the only condition for this to happen is when 3 of them, a, b, and c, are 0, then we can call this collection linearly independent. But if there is a possibility where you see you can have at least one non-zero value a, b, c, this collection is linearly dependent. Okay, that is the idea. Now let's equate. Okay, let's equate. Necessarily, a minus b plus 3c, the first entry must match with 0, the second entry must match with the second one 0, and the third entry must match with the third one. So b plus c is 0. So from this, b is minus c. From the third equation, students, from the third one can obtain simply that b is minus c. And here, if b is minus c, students, look, if b is minus c again, come there. If b is minus c, come here, substitutes that b minus c in place there. Then you are going to have 2b plus c equals 0. So look, 2b plus c comes 0, just adding these two downward, students. Look, student, if you directly add the first two, or subtract the first two, sorry, if you subtract the first two, a minus a is 0. So, yes, students? Look, let me just explain. If you subtract these two, a minus a is 0, and if you subtract upward, a minus a is 0, 2b minus b, 3b, and what's happening here is c minus 3c will be minus 2c. You see, you can have this one. 3b minus 2c equals 0. So from this, one can obtain that b equals c. Okay, b equals c can come. So if b equals c, student, and b is minus c, can equate c with minus c, and you can bring this minus c to the right. C plus c comes 2 times c equals 0. So c comes 0. If c comes 0, students, b also is coming to 0. So b is 0, c is 0. So you can substitute 0, 0 in one of these two. So you will obtain a being 0. So a comes 0. So everything here, or the coefficients a, b, c, look, a, b, c comes 0. It is when all these 3 coefficients are 0 that we can attain this 0. Otherwise, we are unable to obtain, you see, 0 condition, or 0 vector. This shows you that these triple, you see, entries are linearly independent. Okay, so the first is assured. Now what comes next is the case where, what, students? The case where the other is, you see, the case where the spanning condition is going to happen. Okay, the spanning condition is going to happen. So let me show you that. The spanning condition is going to be considered like this. Take an arbitrary element from R cubed. Now, can we construct, okay, can we obtain this element xyz by taking the linear combination of a, b, c using these 3 given components? Let's see that. Look, now we have to unite these 3 and take coefficients a, b, c in order to form xyz. xyz is an arbitrary entry taken from R cube. So do you think that these 3 are building blocks? Do you think that these 3 are bases in order to generate any arbitrary entry in R3? Let's check. So what we need to do is we have to determine a, b, c in terms of xyz, because xyz are, you see, components taken from R3. So we have to look for the case where we can solve a, b, c in terms of xyz. So this is going to be, when you add the left one, you will obtain a minus b plus 3c, a plus 2b plus c, b plus c, and the right one is xyz. So adjust everything as we did before. So we are going to come to this situation. So let's now try to solve for a, b, c. So we are going to determine a, b, c in terms of xyz. So look, from this 3b minus 2c equals y minus x can be obtained. How is this obtained? Just subtract the first two upward. A minus a is 0, 2b minus minus b is 3b, c minus 3c is minus 2c, then y minus x can come, you see. And from the third we have b is z minus c, right? So what comes next is, look, we are having 3b minus 2c is equal to y minus x, here we got, but we know what b is, it is z minus c, so we can substitute that b here. 3z minus c minus 2c equals y minus x. So from this we can have 3z minus 5c, because minus 3c minus 2c makes minus 5c y minus x. Mind you, our intention is to find these three values a, b, c in terms of x, y, z. Now I'm running to solve for c, so c is going to be like this. Now look, y is known, x is known, z is known. You see, x, y, z are given. So your c is going to be negative 1 over 5 of this. Now let's try to come to b. You have been told that b is z minus c, directly taken from the third one. So z is taken as it is, now minus, what is c? C is already obtained here. A matter of taking this one and substituting and evaluating this one, you finally come across with this. So you repeat this, Now c is known, b is known. Can we determine a? Yes, you can substitute in one of the first two expressions or equations. So from the first equation, a is x plus b minus 3c. Just move minus b to the right, 3c to the left. You do have x plus b minus 3c. So x is taken as it is, but we knew what b is. You can copy this one and paste here. And minus 3c is taken, and we knew what c is already obtained there. So as we are operating this, we will finally come across with this kind of expression. So now students, a is obtained, b is obtained, c is obtained. So if you take a, b, c expressions and substitute here, look, a is obtained, b is obtained, c is obtained. So whatever x, y, z, you see, whatever element you may take from R cube, it's a matter of taking a, this one, b, the obtained one, c, you see, the obtained expression, together with these building blocks, these bases, you see, to form this x, y, z. So whatever x, y, z you may take, you see, these three can be building block in order to make this x, y, z. It's a matter of taking a, this expression, b, this expression, c, that expression. For example, if you take x1, y2, and z3, you see, a now can be obtained by using this one, x1, y2, z3. So you will get a certain output for a. Put here y2, x1, z3. Again, you will obtain a certain output for b. And for c2, you can substitute 2, 1, 3 there, and you will obtain a certain number. So let you take these three numbers, a, b, c, and put them here, a in place of a, b, and c. And if you operate that together with this, you will finally obtain 1, 2, 3. So a, b, c are actually coefficients, so we are able to determine any element of R3 in terms of what? In terms of these components. So for any x, y, z, an element of R cubed, as you see, we can write that x, y, z in terms of a, b, c, a times 1, 1, 0, plus b times minus 1 to 1, and c times 3, 1, 1, as you see like this. Okay, I just have substituted the obtained ABC values in place of ABC. Okay, nothing is done. Hence, from these two conditions, we can say that this is a base. In order to know the dimension, we have to know the number of elements within this collection. The number of elements here, as you see in the base, is 3. So the dimension of the given vector space is going to be 3, because the dimension of the vector space is the number of elements in the base. Mind you that the base can be of different kinds, but the number of dimension for a given vector space is fixed, is always the same.